Hey there, everyone. I hope you've all had a safe and pleasant holiday weekend. Today, we're dealing with this monster of a problem. It's a lot of text, I know. On top of that, it's not exactly easy for an introductory physics problem. A good chunk of the challenge here is trying to figure out just what is going on and what we are supposed to do. But that's why I'm here. I've got us covered. Let's get started. Things begin fairly simple here in part A. We need to figure out how many cars these diesel engines can pull. And we can do that by taking the total power available to the engines and dividing that by the pulling power required per car. The power units will cancel out, and our final result will tell us how many cars the train can bring along. The total power is just the full power output of the engines, and the pulling power needed per car is the product of the required horizontal pull per car and the speed that we want the cars to move at. When we plug that into a calculator, you'll get a result slightly larger than 177. Now, we can't pull a quarter of a car along, so we'll have to reduce this to the nearest whole number, which is 177 cars. And we won't break this down using significant figures because we want an exact amount of cars that we can take. So that is our answer to part A. Part B is where the difficulty ramps up a bit. And I think it helps if we draw a picture. Let's start with an angled coordinate system that applies to a train trying to climb a hill at some angle alpha. We can ignore all of the cars from part A for now and just focus on the engines. If we draw the forces involved with the train climbing this hill, we'll have the weight of the engines pointing down and some amount of locomotive force driving the train up and to the right. Since friction wasn't mentioned, let's ignore that as well. Since the weight doesn't lie along the y-axis in this system, we can insert our angle adjacent to the weight vector and break the weight down into its components. If we do the sum of forces in the x direction, we can solve for what the force is by setting the right-hand side equal to 0. Now, before I do that, let's ask ourselves a question here. How can the right-hand side be 0 if the train is accelerating? Well, the train is climbing this hill at a constant speed, at 27 meters per second. So, while the speed of the train isn't changing, the direction will as it climbs this slope. So we're not trying to solve for the extra force to make it move faster. Instead, we want the amount of force needed to allow it to resist gravity at a constant speed as it moves up this hill. We can move the sine component of the weight over to the other side, as well as rewrite the weight in terms of the mass of the engines times g. Additionally, we know what this portion is here. That's our provided 0.1 meters per second squared quantity. When we multiply these two together, we'll get the following amount of force that's needed to keep the train moving steadily on that hill. It's a big number, so let's write it in scientific notation. This is the first part of the answer, but we need to show that it's about the same for the second part. Now, we're told that the angle is equal to the tangent inverse of a 1% slope. Let's take the tangent of both sides here. It doesn't seem like this really does anything, but if we multiply both sides by g, notice that the right-hand side is just about the same acceleration we had before, 0.098 is almost 0.1, which would mean we could cut that g sine alpha out from our force equation and replace it with this g tangent alpha. We should get nearly the same result on our calculator when we multiply it out. And in fact, we do. It's pretty close. When we report it using the same two significant figures, the result is the same that we had before. It's 1.1 times 10 to the 5 newtons. That's it. Let's move on to part C. The extra power needed in the x direction for the train is going to come from the scalar version of our power equation. The locomotive force is the expression we just had with the tangent of alpha in it, and we'll multiply all that by the train's constant velocity of 27 meters per second. Put this in your calculator and truncate the result using two significant figures, and we get the 2.9 megawatts of power that we expected. On to part D. In the first part, when everything was moving horizontally, we had the following equation to solve for the number of cars that the train could pull. But now there's this slope involved, so we'll have to modify this expression. In the numerator, some of the power is lost by keeping the engine at a constant speed up the slope. A similar thing happens in the denominator. Some extra power has to be accounted for every single car to make sure that they don't slide backwards down the hill. When we plug in the numbers and enter that into the calculator, we get a much smaller number of cars this time. Like before, we can't pull a non-integer amount of cars, and we can't round up either, since that would be too many cars for the engines to handle. Instead, we're going to round this down to 35 cars. And that's our answer to part D. This one was a bit long, so let's put our work on the solution card and review. In part A, everything was moving horizontally. So we took the total power provided by the engines and divided it by the required pulling power for each car and found that we could pull 177 of them. In part B, we saw how the sine and tangent identities in our force equation resulted in very similar numbers with a tiny angle involved. And when approximating these two using two significant figures, we get the same result. For part C, we took that force equation with tangent of alpha in it, and we put that in the power equation and matched our expected number of 2.9 megawatts. Finally, in part D, we had to account for the extra power to resist gravity for the engines and each car, resulting in a much smaller number of cars that could be pulled along by the train as it moves up the hill. We're now done. Thanks for watching, everybody. Take care.